thank you. So I thought I would take a page out of Matt Might's book from yesterday and start with a disclaimer. And the disclaimer is that I'm not a lawyer. I don't play one on TV, though I could be convinced to do so. And this presentation and the paper does not constitute legal advice, okay? So don't try this at home, kids. Okay, so what are we talking about here? So we're talking about something called conveyances. In the Anglo-American legal tradition, the rights of property ownership can be transferred between different people using documents that we call deeds of conveyance. These are things like wills or leases that you use to define how property exchanges hands, right? There are different types of these documents, and they have different requirements according to which jurisdiction you're in, but at least in like the Anglo-American tradition, that's the United Kingdom, most of the United States, most of the former colonies of Great Britain. These documents are written in fairly standardized language, and over the past few hundred years, the various judicial bodies in these countries have agreed on what this language means, right? So going forward in this talk, we will be talking about the right to possess. That's something we called an interest. And if the owner of such an interest has the right to possess the property right now, we call it a possessory interest. And if the right to possess is sometime in the future, we call it a future interest. Okay, so let's look at some examples of what I mean. The simplest conveyance looks like something like this. There's some owner O that conveys some piece of property P to some person A, right? So P is being given to A sort of in perpetuity, forever, right? Now, the terms can be limited by some amount of time. Typically, they can be for the life or some duration of whoever is receiving the property. So in this case, it's limited to A's lifetime. But they can also be limited by other events, right? And this set of events is fairly open-ended, right? Anything you can think of, you can sort of write down. And then you can sort of string these future interests along. So you can write down something like this, where A has the right to possess the property while A is alive, but after that it goes to B, right? And you can see how this chaining along can get even more complicated, and how the property flows between different people can depend on different kinds of events. So at this point, you might be thinking, okay, this is all well and fine and seems kind of interesting, but what does this have to do with programming languages, right? Why am I giving this talk at a programming languages conference and not at, say, a law conference or a law school? Well, to figure that out, let's look at two more examples. So here's one, and here's the second one. So who thinks that these two are the equivalent in the same way? Raise your hands. No. Oh, one person. Okay, no one. So this is I think a reason why lawyers and computers and at least PL people could go well together, is because we both write things down in annoyingly painful detail. So in this case, the first statement leads to something like this, right? Where O gives A the right to possession, and as soon as A graduates, B gets it, right? Well, the second one, even though it looks very similar, is actually a little different. In the case that even after A graduates, A still has the right to possession until B actually claims the piece of property, right? So if you were to open up, say, a first-year property law textbook, you might see a table that looks something like this. We're talking about two different kinds of transfers, like we saw in the previous example. One where transfer is immediate, one where transfer requires the owner to actually make a claim. The titles are not really that important. These are just terminology in this field of law. But if you open up this table in the textbook, you'll see something that looks like this, right? The way to distinguish which of these cases a certain conveyance is in depends on these very particular phrasings and punctuations, right? So you have these pretty small syntactic differences, which actually lead to pretty large semantic differences. So that suggests that this is a ripe area for use of a domain-specific language, right? We have a sort of well-defined syntax, we have sort of agreed-upon rules for what that syntax means, and we have a rich language of events and conditions and connectives that ties everything together, okay? So for our work, we took this area of law, specifically these conveyances, and we developed a sort of minimalist core calculus from them. We also developed a surface syntax which looks pretty similar to the natural language used to write these conveyances and documents. We developed a way to translate that surface syntax into this core calculus, and we actually developed two kinds of semantics for it. An operational semantics, which translates very straightforwardly to an actual interpreter that you can run, and a denotational semantics that you can use to write proofs. And these are proofs of things that most property lawyers would agree are common understood principles in the field. And by having the two semantics be equivalent, we can then guarantee that our implementation actually implements something that a practicing lawyer would take to be a faithful embodiment of the principles of the field. All right, so let's go ahead and work through an example. I'll give you a few seconds to read through this, and we'll go through each line in detail and see what it does. Okay, so the first sentence is pretty simple. We're saying that Olive owns some piece of property. For brevity, we've excluded the name of the property going forward. And this just gives us what we'll call an atomic interest, right? So there's one interest, it belongs to Olive. That's it, right? Now things start getting a little complicated. We have this sort of three-part conveyance, right? It's going to three different people at different times, and it's predicated on different conditions. So what we want to end up is something that looks like this, right? You can think of this as an AST or a term in a very simple programming language. But to go from the top to the bottom, we need to do a couple of steps. First, we need to translate the conditions, let's say like Alice for life or until Bob marries, into something that we can sort of decide truth or false about, right? And for cleanliness, we've combined some things like Bob for life and until Bob marries gets put together into a single condition that we can evaluate. And then we take the separate clauses and we connect them together, right? So you should read the then two parts as being simple sequential composition, right? But there are some other connectives that allow for more complicated terms to be built up. And finally, we do something that is not obvious unless you're a legal practitioner. We insert a reversion, right? This is the idea that once you've made a conveyance to someone else, once all those interests have terminated, the property should revert back to the person who owned it previously, right? This is not something you explicitly write down in the conveyance. It's more an agreed upon semantic fact about this area of the law, okay? So now we've gone from that little program on top to this little term over here. And now we can think about how do we want to execute it, right? So we can sort of feed in an event, right? Something that says Alice dies, and we want to see what happens to this term when that event occurs. So we will check the conditions in this term, see if any of them have changed, and if they've changed, that is like become false, we may have to prune away certain branches of this tree and accordingly reorder the tree, okay? So in this case, the Alice dies event will cause while alive Alice to become false. That means that the leftmost branch terminates and needs to be pruned away. And since we don't want sort of a dangling leftmost term for that sequential composition, we'll move the rest of the term up. So we end up with something that looks like this, okay? So now we can do something interesting, which is something that would happen in real life, is that we can interleave these events and the conveyances, right? So in real life, you make a conveyance to someone, some stuff happens, Someone who owns the property may then decide to give it to someone else. More stuff happens, et cetera, et cetera. So we can have another conveyance. In this case, one of the owners of this interest, that's Bob down there, decides to convey away their interest. And so we do what we did a couple slides ago, is that we expand this tree out accordingly, right? Note that we have a condition, but we also have a reversion. And this time, the reversion is back to Bob, who is the person who made that second conveyance, right? And then we can feed on more interesting events. This time it's a little interesting because the condition that changes for Bob marries is actually a little higher up, right? It's not the lowermost condition, but the effect is the same. We'll prune away everything underneath it and rearrange the tree accordingly, okay? So we end up with something like this, right? Now, this is actually an interesting case because you'll notice that even though this is a sequence, there are no conditions involved, right? And what that means is there are no events that actually change this possession tree, right? So no matter what happens, Carol is always going to be the possessor, and Olive is actually never going to come into possession, right? So this is an example of something that is actually fine to write down and would be fine in a legal sense, but it's an example of something you may not want to actually write down because your intent might be that you intended Olive to actually get the property in the first place. So having this sort of a system where you can write down these conveyances, write down sequences of events, and actually see what comes up would be interesting if you're a property law practitioner or a student. Okay, so I don't want to go into the semantics in detail, but we'll take a look at the core calculus. The language we came up with is actually pretty simple. You only have your atomic interests, and you have a couple different ways of combining them that look pretty simple, pretty similar to an imperative programming language. The bottom construct is a little interesting because it allows us to do the kind of pruning away and rewriting trees that we saw a couple slides ago. And we can combine these all together with events that show up in the program, okay? The translation from the natural language to this core calculus is fairly straightforward, but there are a couple interesting little quirks. For example, if you have a natural language statement that says something like P, but if C, then Q, you don't actually translate that using the if form. You actually use the while form, because what that means is that you want sort of P to retain possession as long as C is false, right? So this is an interesting syntactic quirk that first-year law students would struggle with, but by doing this sort of transformation, it comes out pretty nicely, all right? So just to give you a high-level understanding of the semantics, we treat conditions as black boxes, right? In that we don't have a model for how conditions are evaluated. We've hard-coded some conditions that we've come up, but we basically treat them as functions from a series of events to true or false. And we also require a stepping function. So if you have a condition, we should be able to give that condition a single event, and it could change some internal state. And we don't really care how that change is, as long as we can do a string of these and at the end get back some kind of true or false, okay? So we interleave stepping and simplification operations. So this notion of some events happen and some conditions change, we can think of that as stepping some kind of internal state machine of the condition. And then simplification happens when some terms terminate. You end up with a leftmost branch that's just the bottom case, and you have to simplify it away, right? And in this model, getting the possessory interest is actually quite simple, right? You just look at the tree and find the leftmost term, and that's your current possessor, okay? If you've done work with regular expressions and are aware of derivatives, this is very similar to that idea, okay? So let's talk about evaluation for a minute. We're PL people. This is a programming language. So an obvious thing to do is try to prove some theorems about it, right? And we also want to have some kind of an implementation and make sure that the implementation does the right thing for some value of does the right thing. So the theorems in our setting We've chosen a number of principles that legal practitioners would hold as generally valid in this field. There are some things like ownership is always unambiguous, right? You should be able to look at a series of these conveyances, and if you know about what events have occurred, you should be able to unambiguously find one interest that is the current possessor, right? And then there's stuff like conservation, which is, you can't make estates just disappear unless they've been properly terminated in some way. We have like 5 of these theorems, and we've given proofs of these using our denotational semantics that you can refer to in the paper. Okay. We've also developed an implementation with this nice snazzy GUI. It's available online. The link will be at the end. But this is a pretty straightforward implementation of the syntactic translation as well as the operational translation. So you can pretty much take the examples we showed you, put it into our interface, and it will give you a step-by-step progression of the conveyance as it changes in response to events. In order to test this implementation, we looked at a popular property law textbook. This is called Estates and Land and Future Estates. It's used by a number of law schools in the United States. And we took 119 examples of conveyances from the first 6 chapters of this book. We made some small syntactic changes to make it work with our formalization, but 104 of them passed without any issue at all. Of the remainder, 13 we couldn't handle because they required some kind of complicated condition that we didn't want to put the machinery into modeling. But since our system basically leaves an open escape hatch for new conditions, you could easily write your own models of conditions, and this would go through just fine. A couple more fails because they required some extra syntax that would have made the translation harder, and we didn't want to deal with that complication. Okay, so at this point, we have an implementation, we have a semantics. The semantics tell us that the model we've built generally adheres to what practitioners would consider as being correct, and our implementation gives us the expected answers in some cases that are used to teach students today. So one question we should ask ourselves at this point is like, why do this? This is admittedly a kind of a weird, far out thing to do, but personally, I think it's an interesting experiment. For me, at least, it was very interesting to see how legal thinking and computational thinking are sometimes very similar and sometimes completely different, and a lot of times different in ways you wouldn't expect. So we've been talking to some law professors at various schools, and there's some interest in using the implementation possibly as a teaching tool for law students, helping them better understand the concepts and the details involved. And I think it's an interesting starting point for building some notion of proof assistants or explorers for legal reasoning, right? A lot of the kind of reasoning that this tool do is stuff that lawyers or law clerks today have to sit down and do manually. And I think it's interesting to be able to build computational tools that help legal practitioners do this sort of thing and have some sort of confidence that they're getting the right answers back. And I think that's an interesting area for future exploration. Okay, so you can find the papers and the implementation at this website. Feel free to check it out, and let me know if you have questions, comments, or bug reports. Thank you. Yes.
Semi-natural language.
Yes.
What do lawyers think about that?
That's a good question. So a lot of contracts, a lot of like standard contracts you might use are actually fairly standardized, right? A lot of lease agreements basically say the same thing. There are a number of startups these days which will provide you some kind of templating system, right, where they have a couple of normal things that people usually do, and you can sort of fill in the blanks with your own things. I think it's interesting to sort of figure out, okay, what are sort of the rote things that these contracts are doing and try to automate them. I don't think you're going to be able to present programs in a court of law anytime soon. A large part of that is just because these kinds of things have been around for a long time and people generally know how to do it. And so, getting a whole system to change over is hard and takes time. But yeah, there are computational things to do in this area, but they may not take the form that you think that they will. Yeah.
So you talked about this for property law in particular. Can you speak to the broader view of contract law and whether, what challenges and why? Is it did you just choose property law because it seemed like a good choice, or are there other types of contracts that this would not be suited to?
So we chose property law because it's an old enough body of law that a lot of the ambiguities and kinks and details have been worked out, and there's a general understanding of what different syntactic construct and things in the language mean in the scope of the practice of the law. I don't have a good answer for the broader sense. I think one of the problems with contracts, at least in the American setting, is that you can write a contract for pretty much anything, right? And within limits of what is actually legal to do. So I don't know that we want to go to I don't know how we can express that much of a range computationally, especially since most of it deals with things in the real world that you need to assess and decide somehow. There are also practicalities of contracts that are hard to deal with in a computational setting. So one of the benefits of having legal contracts is that you can actually decide, you can sign a contract and then not follow it, right? And then you can leave it up to the legal system to decide what happens. Or even if someone is violating a contract with you, you can decide not to do anything about the violation and let it pass. And so there are these kinds of sort of social safeguards that have come up with actual legal contracts that I think would take a lot of care and thought to replicate in a computational setting. Yeah.
Ted? So I guess my question relates a bit to the last thing you said. So if I assume a system like yours, I probably could use some of the computer science method to find some really weird loopholes in some contracts, right?
Yeah.
Basically saying well, I want to own this, so let's find a loophole that gives me some statements that I have to make true to transfer all ownership to me.
Yeah.
Do you think if your system came up with such a maybe a very complicated loophole, would lawyers accept that? Or would they say, well, this was not how the contract was intended to be?
That's a good point. And I think the answer would be it depends, right? So I think that's a sort of thing that you would eventually have to settle in a court, right? Where one side would make the argument that would be like, yeah, okay, this is what we wrote down, but come on, we all know what we meant. And then the other side would be like, no, you have to follow what the text actually says, and it would be up to the judicial body to decide. Court cases have gone either way. I think, at least when it comes to property law, I think the language and the practices have been standardized to the point that it would, I think most lawyers would say that, these things have been standardized to the point where if you wrote something that had a loophole in it, you should have known better, right? And this tool is sort of an attempt to help you do that, find these loopholes ahead of time. But again, at the end of the day, if you have a disagreement, you go to a court and the court tells you what to do, right? Which is both a good and bad thing about this kind of a legal system, yeah.
Any other questions? I actually have one.
Yes.
So in your evaluation part, I think you tested 100-something cases which supposed to be correct.
Yes.
Right. So
Yep.
have you also tested to find some bugs in a contract?
Right, so just to be clear, we have not tested against like actual real-world cases that went to court. We took examples from a textbook, which are a little simpler because they're teaching examples. We have not tried to find bugs, but something that has happened is in the process of trying to sit down and figure out, okay, what are the semantics? How do we encode this? We have come across cases where we've asked different legal scholars in the fields, like, okay, here's an example, what do you think it would be? And we've gotten different answers, right? So I think the process of doing this has helped us better understand some details of the field and be able to say, okay, like, this is a case that is still considered to be ambiguous. Unfortunately, I don't remember them off the top of my head, but I think that's the closest we've come to actually analyzing a case and finding a real bug. Yeah.
So do you think that some lawyers are going to use your tool as like a cross when they write a new contract and then they want to check the consistency of the new contract they have written?
Yeah, so I think that would be an ideal scenario that like you write your conveyance as your client wants it to be, and then you use this sort of a tool to figure out if it actually does what the client wants it to do. You can imagine developing something like a model checker on top of this, where sort of it tries to find you a counterexample that violates whatever condition that you want, right? So you might have a condition that is like, oh, I want to guarantee that at some point my grandchildren will always get my house. And you could build a tool that generates a counterexample for when that doesn't happen. So, yeah.
Okay. So anything else? Next speaker.
All right, thank you.